Welcome to The Explainer. Today, we're going to be dissecting the actual, concrete engineering toolkit behind first principles thinking. We're taking what's honestly become a bit of a popular buzzword and translating it into actionable industrial science. Because listen, first principles thinking, it's not just some philosophical concept you chat about at a coffee shop. It's a rigorous, hard-hitting methodology used to literally tear down assumptions, completely strip away industry dogma, and rebuild solutions from the absolute ground up. Let's get into it.
So to really understand this, let's kick things off with a pretty fascinating question. Why did humanity invent the wheeled chariot in ancient Rome, roughly 2,000 years ago, but then wait all the way until 1970 to put wheels on a luggage suitcase? I mean, really think about that delay for a second. Ancient soldiers were out there hauling heavy leather bags of grain, while simultaneously driving wheeled chariots into battle. Yet it took literal millennia before Bernard Sato finally invented the rolling luggage that we all use today. How crazy is that? Well, what this brilliantly illustrates is the cognitive trap of confusing form with function. See, for decades, innovators were totally stuck trying to optimize the form of a bag. They were, adding zippers or maybe swapping to lighter nylon, but they totally ignored optimizing the actual function, which is simply moving a heavy object with less effort.
Which brings us to Section 1, Escaping the Analogy Trap.
Okay, so that massive historical delay with the luggage, it perfectly exposes this fundamental flaw in how our brains naturally work. It's called reasoning by analogy, and it's basically our default mode. It mimics existing forms, it heavily relies on industry conventions, and it mostly just makes incremental changes. Honestly, it requires incredibly low cognitive energy because, well, you're just copying and tweaking what's already out there. But then you contrast this with first principles thinking. Now, this is an entirely different beast. This approach deconstructs a system all the way down to its objective physical truths, those core things that absolutely cannot be argued with, and then optimizes the core function from right there at the bottom. It strips away the outer form to build a highly disruptive, entirely new solution. Basically, it forces you to stop copying the compromised designs of the past.
But I want to be super clear here. This methodology is not easy. It requires intense cognitive weight. As Albert Einstein so famously pointed out, if I had an hour to solve a problem, I'd spend 55 minutes thinking about the problem and 5 minutes thinking about solutions. And first principles thinking demands exactly this. It demands systematic doubt. You literally have to spend your energy defining the absolute base problem and identifying the fundamental physical limits before you even begin to entertain a possible solution. All right, moving right along, let's look at Section 2, the idiot index.
So to actually quantify this kind of philosophical concept out there in the real industrial world, Elon Musk introduced this brutal but honestly incredibly effective diagnostic tool. He calls it the idiot index. You calculate it by taking the final purchasing price of a manufactured component and simply dividing it by the spot market price of its raw constituent materials. Walk through this with me. If the final price of a part is vastly higher than the basic cost of the raw aluminum or steel it's made of, well, you're going to get a high index score. And a high score exposes extreme bloat. It shines a giant spotlight on middleman markups, inefficient processing paths, completely unnecessary logistics, and all that bureaucratic red tape just waiting to be disrupted.
Let me give you a genuinely shocking example. 65. Back in the early days of SpaceX, the engineering team realized they needed this rocket component called a half-nozzle jacket. So, an external supplier quotes them $13,000. But when the team looked at the raw physical materials, literally just the steel, it was only worth $200 on the commodity market. Run the math, and that results in an absolutely incredible idiot index of 65. That means you're paying 65 times the absolute physical limit of the materials themselves. This brutal realization is exactly what forced SpaceX to totally abandon external procurement for that part and aggressively switch to internal vertical integration and autonomous manufacturing. No way they were paying that markup.
And the thing is, this brilliantly illustrates a concept that goes way beyond aerospace. Look at early rocket launches. A $65 million price tag stood against just $1.3 million in raw materials. That's an index of 50. But you also see this exact same thing happening in software engineering. Open source software often suffers from massive feature creep and over-engineered third-party API integrations, which leads to this bloated, high-index final product. Even in your everyday procurement, right? If you buy directly from a factory, you instantly bypass those 30 to 50% retail markups, essentially dropping your idiot index from 2.0 down to near 1. It is a wildly universal tool for identifying cost creep.
Now on to Section 3, the 5-step algorithm. So to actively hunt down and fix these high idiot index processes directly on the production floor, Musk relies on a very rigid system. It's designed to ruthlessly eliminate organizational entropy. Let's walk through these 5 steps. Step 1. Question every requirement. Every single rule must have a specific person's name attached to it so you can directly challenge them. You never, ever accept rules from some abstract department. Step 2. Delete parts or processes. And you must delete so aggressively that you eventually have to add maybe 10% back. Seriously, if you aren't forced to add things back, your initial deletions just weren't aggressive enough. Step 3. Simplify and optimize. Crucially, this has to come after deleting. You don't want to accidentally optimize a part that shouldn't even exist in the first place. Step 4. Accelerate cycle time. Move faster, but only after you've streamlined. And finally, Step 5. Automate. Automation must strictly be the final step, never the starting point.
Which leads us nicely into Section 4, disrupting aerospace and auto.
Let's actually look at how applying these exact steps radically altered the physical materials chosen by the entire aerospace industry. Let's take the Starship project as an example. For a long time, the industry consensus was basically that advanced carbon fiber was the future, period. But when they applied first principles analysis to the extreme physical limits, it revealed a completely different story. Out in deep space, temperatures plunged to -270 degrees Celsius. And in that kind of extreme cold, carbon fiber actually becomes super brittle and starts forming microcracks. But, and here's the crazy part, 304L stainless steel does the exact opposite. It doesn't embrittle at all. In fact, its tensile strength and toughness actually surge by 50%. Plus, the steel only costs about $3 a kilogram compared to carbon fiber's $200. It was a total paradigm shift based purely on unarguable physics. And this massive material pivot unlocked a totally fascinating, brand new engineering innovation: transpiration cooling. See, because stainless steel can easily withstand atmospheric reentry temperatures of over 800 degrees Celsius without losing its strength, engineers realized they could design a double-layered steel shell. What they do is pump liquid through microscopic pores, basically weeping the liquid out to the surface to create this protective thermal gas shield through evaporation. I mean, this is physically impossible to do with fragile carbon fiber, and it saves massive vehicle weight because it drastically reduces the need for heavy, clunky heat shields.
Now, this physical deconstruction applies just as effectively to the auto industry, too. Let's contrast traditional auto manufacturing with Tesla's gigacasting. Your traditional car chassis is stitched together from over 120 separate stamped parts, and it relies on thousands and thousands of welds. That naturally introduces high-tolerance errors and requires a massive factory footprint to pull off. Gigacasting, on the other hand, replaces all of that with one single massive cast piece, zero joints, extremely high geometric precision. It's basically the ultimate expression of step 2 of the algorithm: delete parts, just get rid of them.
The actual structural execution behind this is staggering. We're talking about giant machines delivering up to 6,200 tons of clamping force, literally injecting molten aluminum at an incredible 36 kilometers per hour. And to prevent microscopic air pockets from forming, they use a high-tech micro-vacuum injection system. They even went so far as to formulate a custom AA386 alloy that achieves its required strength immediately upon cooling. That lets them entirely skip the high-temperature heat treatments that usually cause dimensional warping. Oh, and because electric vehicles obviously don't need to block engine fire and noise, they just ruthlessly deleted the traditional heavy metal firewall completely.
All right, finally, let's tackle Section 5, the limits of innovation.
Now, we do need a crucial reality check here. First principles thinking provides an incredibly clear roadmap, absolutely, but it cannot magically bypass the brutal laws of material science. A perfect example of this is the 4680 battery project. The goal was to drastically lower battery costs using first principles, but man, they hit some severe microphysical roadblocks. Creating a tabless battery design to reduce heat, well, that required extreme precision laser welding, which ended up causing massive manufacturing headaches. Furthermore, their dry cathode manufacturing process, which involved mixing dry PTFE powder to avoid toxic wet solvents, resulted in micro-tearing and severe dusting where the electrode material would literally just crumble apart. They also faced a really high initial capacity loss due to unstable chemical reactions. These brutal physical realities caused massive multi-year delays from 2021 all the way to 2024.
Overcoming these absolute limits required years of painful trial and error. To finally solve the dusting and tearing issue, they had to invent a completely new microscopic solution. They ended up using high-shear jet milling to create tiny spiderweb structures. This incredible process whips the polymers into a flexible 3D web that physically binds the dry powders together, allowing it to actually survive the high-tension rolling process without cracking. They also had to invent entirely new polymer coatings just to block those unstable chemical reactions we talked about. So while first principles pointed the way, the brutal, tedious, everyday work of material science was still 100% required to actually manufacture the thing.
So I want to leave you with this. Look at your own business, look at your own projects, or hey, even just your daily routines. Where is your highest idiot index? Where are you paying a massive premium in time, money, or energy compared to the raw core value you're actually getting back? And more importantly, how can you use the 5-step algorithm we talked about to strip that process down to its absolute core function? Try it. Challenge your assumptions, delete the redundant parts, and build your solutions upward from fundamental truths. Thank you so much for joining me on this explainer, and I really hope this radically changes how you tackle the problems in front of you. Catch you next time.